Right. Let's go to the next topic. Is now we know how to do the expansion of the uh, operator, which is basically this guy, the a new, which is wherever I go. Just this one. This one is defined. Yeah. And now if we have a joint operator with respect to that associated with A, then we want to do a matrix, a basis expansion of that adjoint also. So we'll see what that is. And the idea is that we go back to the definition of adjoint, so, which is involving two functions. Now we're actually using psi and chi instead of f and g, which is fine. So a and a on chi, right? I mean, you can, if you don't like the direct notation, you can add another bar here that which is, it doesn't matter whether you have a bar or not. The original one is just a operator and so chi, and then do a scalar product inside. Where that is by our definition, it's the a, no, a that the operator inside, and then the scalar product chi. This is the definition of a, exactly, right? And then now we use the definition of scalar product, which is saying that you can swap these two elements and then just do a complex conjugate. So that is the same as inductive sine. The next one is just basically this is equals to that. We can now take the complex conjugate of this thing and we recover this one. All right, so inductive sine. It's just now you take the complex conjugate of this one, you get back to this one, which is the complex conjugate of this one. So, complex conjugate. So now and you can use the direct trick using this one, right? So you have this A is given by this one. So we need to take a complex conjugate later by sum over mu and u psi, and then the rest of this A, which is by mu a mu mu and chi. Right? So that is this one, and then the complex conjugate. Okay, and now the rest is you can just take the complex conjugate of individual one. So this is okay. So next step, right? Instead of writing another step, just everything complex conjugate. Okay, that's fine. And now the the idea is to write it in reverse order. This complex conjugate, you use the property of the scalar product. You just interchange the position and get rid of the complex conjugate. Likewise, this one, and then these are number. You can put one to the others in exchange the position also. And then you have the mu mu mu. This becomes that one. This becomes that one. Right now, this is in the form just like what we did in A. So A is summing over. So so this part summation, and this part is just like this one. except that now this is for the adjoint, right? The adjoint. So the adjoint, you can say this is the representation of the adjoint, or you can write it like here. So adjoint is some mu over mu and mu, or mu or mu, doesn't matter. You know, mu and mu. And I mean, this is like this one, but then to compare with the original one, you want new here and new here. Basically, in this case, you uh, just interchange mu and new, because these are just dummy variables. You can call mu and your new, call new your mu, right? Then you interchange this position, becomes mu new by mu. All right. So this A is given by that. A dagger is given by that. Right? So the adjoint is like the A, except that the matrix elements change. Instead of A new mu, you become A complex conjugate mu new. So you do two things. One is complex conjugate, the other exchanging the position, which is the way to do transpose of a matrix. You interchange the first and the second index of a square matrix, you get the transpose, right? Um, so that is the explicit way of relating the adjoint operator to the original operator. Once you do a matrix representation, or what we call a basis expansion, then all you need to do is just do the transpose and the complex conjugate, and that is how you get this A. So that is the same as the what we do the matrix, that is called the adjoint matrix also. Okay, so that is not difficult. It's okay. So up to here. So this one of the more important results is that we define uh, the adjoint by this definition. Now after the the basis expansion, now we realize that we can do we can get the adjoint by simply changing the matrix element to the complex conjugate transpose of the matrix element. Okay, and now the property of Hermitian becomes if it's Hermitian, so A nu mu will be equals to A mu mu. This becomes the condition of Hermitian. So any Hermitian operator will need to satisfy it, right? And that is also the same as the definition of Hermitian matrix. If Hermitian and Hermitian, then to satisfy this condition. If all the elements are real, this means this is just symmetric. So real matrix or Hermitian is just become symmetric. Okay, and likewise, if if the if the matrix is unitary, then this Hermitian or the complex conjugate transpose becomes the elements of the inverse, right? Instead of the yeah.
Unity means determining this one.
Yes, later on we'll do that. We'll determine that that's the case. I think a couple of sections later we'll have that unitary. Talk about the expansion of unitary matrix. The unitary matrix expansion, the matrix element is slightly different. Define it, but afterward you get the property that the determinant is one.